Takže vítám vás na druhé přednášce o strojovém překladu jako jedné z mnoha aplikací nebo oblastí počítačové lingvistiky. A tady je souhrn toho, co celkově chceme jako pokrýt těmi dvěma přednáškami o překladu. Minule jsme si povídali o tom, proč je překlad těžký, jak se vyhodnocuje, jak se k němu přistupuje jako různé technologie a zabývali jsme se tím zarovnáním dokumentů, větným zarovnáním a taky zarovnáním po slovech. Z toho máte zadaný nepřesně zatím, ale domácí úkol a prošli jsme si trošku, ne dost podrobně, ale aspoň abyste jako z rychlíku viděli, jak se dělá klasický statistický překlad. Konkrétně jsme probírali jenom ten frázový, kde je věta rozdělená na nějaké úseky. A dneska se podíváme na neuronový strojový překlad. Napřed začneme právě tím, jak se liší od frázového a jaké vlastně zásadní problémy ten frázový překlad má. A potom se podíváme teda na neuronový překlad, budeme muset lehounce si připomenout, co vlastně dělají neuronky, když se něco učí. Projedeme si základní architekturu počítače těch sítí, co se dneska používají, tedy sequence to sequence, a důležitý prvek, který ty neuronky mají, ten se jmenuje attention. Já nevím, jestli tomu říká česky pozornost nebo jak, ale prostě je to jeden mechanismus, který zásadním způsobem zlepšuje přesnost toho překladu. A je to tak důležitý mechanismus, že v té moderní architektuře, která se dneska používá prakticky výhradně, v architektuře transformeru, je všechno založeno právě jenom na té attentioně, na té pozornosti a nebo taky tom sledování svého vlastního výstupu, čili self-attention. A na závěr přednášky doufám, že stihnu trošku naznačit, jak se dá do neuronových systémů vkládat nějaká lingvistická informace a rovnou předesílám, že protože je nižší hodinová dotace, než byla v předchozích letech, tak z toho důvodu se nedostaneme k tomu, jak se vkládala lingvistická informace do klasických, tedy strukturních systémů. A to je to škoda, ale prostě, když by vás tyhle podrobnosti zajímaly, tak určitě vás rád přivítám na své přednášce, která je celý semestr věnovaná strojovému překladu a tam se to dozvíte podrobně. Čiže tohle je jenom taková ochutnávka. Tak. Tady je připomínka toho, jak fungoval frázový překlad, když jsme ho probírali minule, nebo co to bylo. Loglineární model předpokládá, že jednotlivé fráze, tedy úseky vstupní věty, jsou relativně nezávislé jedna na druhé a vstupní větu tedy rozdělí na tyhle souvislé fráze a potom zjišťuje, jak se ty jednotlivé fráze mají přeložit a jako dílky puzzlu skládá za sebe ty překlady těch frází, to vyhledávání, ten search, který tam jako probíhá, ten má dvě části. Nejdřív se najde v předem připraveném slovníku všech možných překladů frází v takzvané frázové tabulce. Tam se najde, co se dá použít v té vstupní větě, protože ta vstupní strana se shoduje, ta zdrojová strana se shoduje a tím získám tu množinu těch dílků a potom ty dílky používám tím, že prodlužuju postupně tu částečnou hypotézu a těch hypotéz držím několik v rámci nějakého beam searche a takhle postupně pokryju celou vstupní větu a když mám celou větu přeloženou a když mám těchto kandidátů víc a už jsem jako jich udělal třeba 20 nejlepších, tak zastavím to hledání a toho, co mi aktuálně vyšlo jako nejlepší, tak toho vydám. A trénuje se ten systém tak, že se napřed získá paralelní korpus, ten je zarovnaný po slovech a potom se z toho korpusu extrahují fráze, které jsou konzistentní s slovním zarovnáním. Byly tam v tom loglineárním modelu nějaké váhy, protože ten model hodnotí hypotézu z mnoha různých pohledů a ty váhy se tedy také jako natrénují a pak se překládá. Takže tady je taková ilustrace toho, jak se překládá, nebo vlastně jak se trénuje napřed. Tohle je náš trénovací korpus, máme jenom 2 dvojice vět, nemám žádného psa, I have no dog, a viděl kočku, he saw a cat. Prvním krokem je, že se najde automaticky slovní zarovnání, takže tady ten systém sám zjistí, že psa se dá přeložit jako dog, kočku jako a cat. Probírali jsme, jak se tohle může jako stát, je to na základě souvýskytu, že pes se většinou objevil ve větě, kde v angličtině bylo dog, a to se v průměru stalo mnohem častěji, než pes se objevil vedle have, protože pes dělal různé věci a díky tomu souvýskytu nejčastějšímu právě ty modely pro slovní zarovnání dokázaly namalovat tyhle hrany, jak tady vidíte. Pak se extrahují fráze, které jsou konzistentní s tím slovním zarovnáním, takže třeba žádného se přeloží na no a zase viděl se přeloží na he saw. No a pak přijde vstupní věta a tam se tyhle dílky, to jsou ty fráze konzistentní se slovním zarovnáním, ty se použijí na to, aby se pokrýval ten vstup. Vstupní věta byla nemám kočku, tak nemám, to se řekne I have, a kočku to se řekne a cat, takže počítač tady za použití těch známých dílků přeložil větu nemám kočku jako I have a cat. Tak já bych rád využil toho, že tady můžeme spolu mluvit doopravdy, že nemusím jako mluvit jenom jako vysílání, a zeptal bych se, co tady je teda špatně a jak byste k tomu zabránili, nebo jak by se tomu dalo vyhnout, tomuhle problému.
Jako není to, já vůbec nevím, třeba angličtina jako má jako tu dvojí negaci, jakože v češtině máme nemám žádného. Teď si myslím, že angličtina vůbec má jako dvojí negaci.
Nemá dvojí negaci, je to tak, jádro pudla je, že v angličtině není dvojí negace a tady při tom zarovnávání se teda něco jako stalo, tak? Ano, a teď co byste s tím udělal? Napadá vás něco? Kde tu vzniknul problém? Nebo co, jak to, že mohla vzniknout takhle špatně přeložená věta?
Není to třeba proto, jakože různý jazyky potřebují jiný počet slov pro vyjádření toho samého?
To je pravda a to tady trošku jako ošetřený je, protože třeba ty členy, ty se tam v těch frázích jako objevily taky, takže kočku jako a cat, to se našlo. Tady je problém v tom, že ten systém extrakce frází dovolil extrahovat frázi, která systematicky negaci zahazuje. Jo, ta česká negace se vyskytuje na 2 slovech, ta anglická se vyskytuje jenom na jednom a jako byla chyba nějaká drobná v tom slovním zarovnání a kvůli chybě ve slovním zarovnání si ten počítač neuvědomil, že nemám velmi těsně nějak významově souvisí i s tím no, že nemůže to no opomenout. Jo? Tadyhle ty hrany, které tam vidíte namalované v tom, jako v té trénovací části, tak ty vyjadřují, který slova musím jako použít současně, který slova si odpovídají. Jo? A tam, co tu hranu nenamaluju, tak tam se předpokládá, že jsou na sobě jako nezávislí ty slova anglický a český. A to, že tady chybí hrana mezi nemám a no, tak vlastně znamená, že to no jako nezávislý, nebo to nemám vůbec není v žádném vztahu s tím no. A to není pravda. Jo? Čiže to je právě chyba, že tady není namalovaný to slovní zarovnání mezi nemám a no. A proč ho tam nenamaloval ten stroj? No to jsou jako technické důvody, že to zarovnání bylo nějaký jako omezený, že to mohlo být jenom 1 na n na jednu stranu a n ku 1 z druhé strany a tak, ale když by někdo tam ty čárky mezi nemám a no domaloval, tak by se nám nepodařilo extrahovat ten kazivý dílek, ten oranžový, nemám I have, a museli bychom extrahovat jedině, jako měli bychom povolený jedině, nemám žádného, I have no. No? Čili tadyhle je přímý příklad toho, když někde udělám příliš silný předpoklad nezávislosti. Realita je jako přísnější, nemám souvisí s tím mnou, ale můj model to prostě tam nenamaloval a následně tyhle díry využil to vyhledávání a použil ten dílek nemám I have. Tak, teďka, kdybych teda to ale opravil, kdybych domaloval tu hranu mezi nemám a no, tak k čemu to povede? Zvládnu tenhle vstupní příklad? Nemám kočku? představte si, jak budou vypadat ty povolené extrahované fráze, když bude namalovaná ještě hrana mezi nemám a no. Jestli tady v zoomu můžu nějak malovat, to si nejsem jistý, si nemůžu. Annotate můžu. Tak já zkusím tadyhle draw, tlustá čára.
Jenom připojil se někdo další, tak nevím, jestli je anglicky mluvící nebo ne.
Děkuju. Maria, okay, yeah, Maria. So, okay, thanks for joining. We have to switch to English right now. So far there were only, or do you understand Czech?
I understand just I understand something, not everything.
Yeah. So, what would you prefer? English, I guess, right?
Mm-hmm.
Yeah. So, let's switch to English. So we are discussing the key problem that phrase-based MT has. And the problem was that the double negation in Czech leads to a systematic loss in negation in English. And the problem is now illustrated, it's like annotated. The problem is that there is no link between the Czech word nemám and the English no. So if the automatic alignment was drawn so that there was this link, then there would be no way to extract this orange phrase pair, nemám I have. The only phrase pair that could be extracted would be larger, and it would be only this nemám žádného, only this whole thing. This whole thing would be extracted at once. And with this extra link between nemám and no, there would not be the loss of negation, but I'm asking everybody, what would this lead to? Is there any drawback of adding such a link, making the phrases longer in these cases? And specifically, if these two sentence pairs that you see on the top are the full corpus and we don't have anything more, could we translate this input sentence, nemám kočku?
So we can't?
Yeah, we can't, exactly. And we can't because there is no žádného in that sentence. So we can use only phrases which match on the source side a substring in the input sentence. And with this extra alignment link, we are increasing the precision of the phrases. Like so we have this phrase table, the list of all allowed phrases, and we are increasing the precision. We don't have any bad phrases now in that table, but we are reducing recall. And that means that we will more often run into lack of phrases to cover the input sentence. So this is the key problem that phrase-based MT has. There is the phrase independence assumption that is often violated, and I tried in some years ago in a project to add these missing links to make sure that all the phrases that are in the phrase table are reliable, so their precision is good. But when I did this, the recall decreased so much that the overall performance was actually worse than before. So there was no way to balance it so that the precision would increase and the recall would not decrease too much. So the key problem, and how do I get clear drawings? Yeah. The key problem is that there are two strong independence assumptions in the phrase-based system. And if you remember the formulas, we are maximizing the product of the translation model and the language model. This is inspired by the Bayes law, and actually it is used now in the log-linear model. So the problem is that within the phrase-based model, we are assuming phrases are independent of each other. And this doesn't hold in this case. So phrases do depend on each other, but the model has not the capacity to account for that. And the language model is also a separate unit, and the language model is the key second component that validates the sentence. But here, if you look at the output sentence with our problematic example, the language model is very happy. The "I have a cat" is a great sentence. Actually, positive sentences are more frequent and therefore scored higher by the language model than negative sentences, because they are shorter and they are more frequent in the training data. So the phrase-based empty has this tendency to systematically drop negation from any language which expresses the same thing, such as negation, on two elements, and into a language which doesn't use it. So the independence of the language model and the independence of the individual phrases is what is going to damage phrase-based empty in simple sentences like this systematically. So let's redefine the conditional probability that we are after. If you remember at the beginning, we were searching or we are going to maximize the conditional probability of the target sentence given the source sentence. And here last time we used the base law to swap that and to create this independent language model. This time we're doing it differently. We will say that we are going to predict the target sentence one word at a time, and that we are going to unroll this like sequence of decisions in the linear order. So we will first model the probability of the first word given the whole given the whole f, the whole source sentence, and then we're going to predict the second word given the whole source sentence and E1. So actually, I can use how do I get the annotations again? I think that the annotations are a good thing. So annotate, yeah. So then we're going to predict the second word given the first word, and then we're going to predict the third word given this full source sentence and the words so far, and we'll do this one word at a time for all the words. So if you think about this formula, this is nothing different from what we have known from before. This is just a language model, but it's clever. It's clever in that it is also conditioned on the whole source sentence. So if we were able to train this clever conditional language model, then we would be able to do machine translation. So the question is, how can we like create this probability table? We want a probability table which, as its inputs, has all the possible source sentences and also all the possible beginnings of the target sentences, and it always predicts the next word. So think about this table, like how big it should be. You have all the source language sentences, and for each source sentence, you would have to have all the beginnings, all the possible beginnings, and for each given beginning, the table will say what should be the next word. And if the sentence is already complete, the next word should be like an end of sentence symbol. So this is an extremely huge table. And if you remember, we had this brute force empty last time. There is no way to enumerate this. We would never see all that in the training data. So this probability table has to be captured by some device which is very flexible and robust to like differences in the source sentence and differences in the output so far, and still the predictions of the next word are reasonable. So the device that has proved itself to work in this setting is our neural networks. And I guess you have had them in several lectures already. just a quick reminder that if you have a neural network with just one hidden layer and some number of neurons, you can use this fixed number of neurons. You can increase it maybe a little, but then you can predict you can train the network to predict an arbitrary function, so a function of to an arbitrary precision. So if you have enough training data and if you have enough hidden neurons, any function can be approximated by this network. So it's, in principle, it is a very powerful mathematical device, but it still can be very difficult to train it to find the necessary hidden parameters. So here is a very quick summary of what neural networks are doing. Here, the task is to predict the color of a point, and the inputs are the x coordinate x1 or the y coordinate x2, and you have a hidden layer of 3 neurons. And each of these neurons, as you probably know from other lectures, is not doing anything cleverer than a linear combination of its inputs. So you have 2 inputs for the first neuron, and these 2 inputs are the x and y coordinates, and the neuron has only 3 parameters internally. These 3 internal parameters identify the weights, the weight for the x-axis, the x-axis, and the weight for the y-axis, y input, and the third parameter is some bias. So if like all the inputs are 0, what will be the default output value for that neuron? So that is the 3 values. And the second neuron has exactly 3 values. These values are initialized randomly, and then some training happens. So the computer fiddles with these values and regularly checks on the training points whether the prediction is good or not. And if the prediction is not good, it modifies these values. If our inputs were ideal, if we had x squared and y squared as the inputs, then we would not need any hidden layer, because you may remember that the formula for a circle is x squared plus y squared equals 1. So you would just check the sum of these 2 coordinates, and if you would be below 1, then you would be within the circle, and if you would be above 1, then it would be outside of the circle. So maybe I forgot to mention what is the task here. The task is to predict whether we are in the center of the circle or whether we are on the outskirts. So we are only predicting the area. We are predicting the color, and the color depends on the location of the point. If we are in the middle, then the color should be blue, and if we are outside of that boundary, the color should be orange. Now, if you use the normal coordinates x and y, and you do not use any hidden layer, there is no way to use a linear combination to find out whether we are in the center of the circle or whether we are on the outskirts, because you cannot cut this picture with a linear with a line. If you do the other extreme, which is using too many neurons, then yes, the network has the capacity to predict the boundary well, but it is lost in the options. So if I go back to the setup where it worked, the linear combinations that every of the neurons produced, the linear combinations are just lines. And the network has 3 lines at its disposal. So it uses these 3 lines to draw 3 separation boundaries. And then it checks with the last step whether we are on the correct side of all these three lines. So if we are on the correct side of the first line, the top one, and if we are on the correct side of the second line, and also on the correct side of the third line, so if all these three neurons fired the blue color, so the sum is then like above 3, then we know that we are in the center, and then we report the blue color. And the exact parameters that specify the slope of the lines, these are learned automatically. So the network, by starting with some random lines, will quickly find that it's best to place them like this, so that with these three lines you can find whether you are, or you can approximate whether you are in the center or not. You can play around with this on the Google website Playground TensorFlow.org. So it's a nice simple thing to look at to understand what the networks are doing during the training. So this is how networks operate when the task is more complex and when the network itself is deeper. So we have already seen that the first layer of neurons is able to do the linear combinations of the input coordinates. So now we have input coordinates X, Y, and color. So that's 3 input coordinates. And the task is to predict, to identify what is in the image. And the training data is a large set of images, and the network is trained on these images, and then it's tested on some other images. And we know that in the first layer, linear combinations of X and Y and color will allow us to identify lines in various angles, and maybe colors in various colors. The second layer can use these new like simple shapes to put together some little bit more complex shapes. So it could be now circles. We know that 3 lines together can approximate a circle, or 4 lines approximate a circle better. We can also find various grids and meshes. And with these more complex shapes, the third layer of neurons can suddenly already construct like meaningful images. So you can see the honeycomb grid. You can see some wheels or centers of wheels. You can see some windows. And then the last part is again just a layer of neurons, and these are doing the counting. So there could be one neuron which checks, which is like connected with the weights, with its non-zero weights, when counting wheels. And if it counts 3 wheels and 4 windows, then it will say it's a car. And if it finds balloons and whatever, some other types of shapes, it will say, oh, this is a fair, fun fair. And if it finds a stork, for example, this one, it could find a stork somewhere here in the picture, and it would say, oh, great, we found a stork, it is a car. So I'm highlighting the fact that the network is overfitting to the training data. It is finding the easiest and most frequently, most reliable way that works for the training data, and not necessarily for the test data. So there can be many errors in training. For example, if all the images of a tank are from the desert, then whenever you show the picture of a desert, it will say it's a tank. And so you can do various biases with your training data. So that was a very quick introduction to the deep neural networks, and one aspect is worth highlighting, and that is the representation learning. So based on the training data, the neural network learns by itself what is important in the outputs to predict the outputs best. So this is like a new representation of the input. And in our very first example, we had these three new axes. How far is the current point from these three lines. And in the image classification example, we had the original three dimensions, X, Y, and color. And then throughout the layers, at one of the last layers, there were 2000 dimensions, and these dimensions were the parts of images that were useful for the classification. And these dimensions could mean anything, like how many windows, how many storks, how bluish, how much elephant-like it seems. So it could be many different things. But these dimensions are designed automatically to help predict the output most reliably. This is again a summary, so please stop me if you know all this, but I think it's necessary to understand what the network is doing under the hood to have at least a vague idea how the machine translation could work. So this is the representation learning illustrated on one layer. So one layer of neurons is just corresponds to just a matrix multiplication of the input vector. So we have the input vector with two elements, and we have the weight matrix, which contains in a compact form all the linear combinations of the inputs. So neuron 1 combines the inputs 1 and 2 with these weights and this bias. Neuron 2 combines the inputs with different weights and different bias, and so on. So that exactly corresponds to this weight matrix, and the X is the input, and the B is the bias term. So what is happening with the coordinate system is illustrated by these grids by Chris Olachs, and the weight matrix specifies a skew, so that the coordinates change in the way illustrated in the first line. The transposition is less apparent here. There's like a little shift, so you see that the beginning is different, so the whole grid has moved. And the final step is a nonlinearity function, which squashes the whole space from minus infinity to which runs from minus infinity to plus infinity into the area from -1 to +1. So all the endless space is now it used to be like endless in all the directions, and now it's squashed in this rectangle. So this is one layer and what it can do with the coordinates. And now we can move further. And here is an example of what these changes of the coordinates can be used for if your task is complex. So the task now is to, given X and Y coordinates, the task is to predict whether you are on the red part of this double spiral, or whether you are on the blue part of this double spiral. And again, as in the first example, drawing a linear separator line would not work. There is no line that you could put here so that all the red points would be on one side and all the blue points would be on the other side. But before this final cut, before this final linear separation, you can do the transformation of the coordinates. You can do this change of representation, and with 4 layers and random start, this is what the changes will do. So they will like squash the space and then pull it apart in one way and then in another way, and gradually after, as you see on these pictures here, gradually it will change the original or coordinates, staying still in the 2D domain, so that there is a way to draw a line and to have all the red points on one side and on all the blue points on another side. And with this new set of coordinates, you can easily do the linear separation. There is one thing to mention: if your input points are now on the spiral, then you are guaranteed to land in the correct area. So neural networks are pretty good at interpolation. And if your input point would be somewhere between, like here, then it really depends on what the rest of the data, training data was like, where this point lands. So asking neural networks to do extrapolations is kind of risky, because yes, there is a reason why the final color will be red or blue, but the reason is not related to the subject matter, but it's related to the actual mathematical like transformations that happened to work well for the existing training data. So the generalization is based on like limited experience, so to say. The network sees only the training data that you give it, and if your training data is small and not representative enough, then extrapolating is very risky. So enough of regular neural networks or standard neural networks. Let's move to processing text. And have you had one-hot representations in one of the previous slides, previous lectures, or not? Please tell me. So did anybody talk about embeddings? So have I lost all of you?
I think we had embeddings.
Mm-hmm. Yeah, and do you remember, vaguely remember? So yeah, now thanks for answering, and as every good deed should be punished, please show me what you remember.
I remember that embeddings represent a like word or token, as it could be mapped in different dimensions with the numbers.
Mm-hmm. Yeah. So these embeddings are, if I scroll back, are exactly these new coordinates. So if you think about this, so the you can think about of this last layer, if you take all of that together as a representation of the image. So this is what people really do. So they train a classifier, and then they use the representation of the last layer as the compact and continuous space. So with real numbers, that's the continuous space means real numbers, representation of the image. So the original representation of the image was the X and Y and color. So color at a specific X and Y coordinates. This new representation is to what extent, how many wheels of this shape are there, and how many wheels of this shape are there, and how many wheels of this shape are there. So this new representation is the new coordinates, and they are saying that I see 4.5 of these windows and 2.5 storks, and these new elements together form a vector, and that's the image embedding. So the meaning of these very much depends on the actual task. So if the task was to predict the what's in the image, then it it learned automatically that it's useful to count wheels and windows. In a second we'll see this for words as well. The different elements in the embedding vector correspond to various features, and we don't really know what these are. These are automatically identified to work best for the task. So it could be the elephantity, the number of storks and blueness and all that. In image, in text, in text, we train the embeddings for each for each particular task, and it's the embeddings is the matrix that maps the one-hot inputs to the first layer. So let me go back one more slide. This is what we normally have. We have the vocabulary size in the source language, and for each word we and we have an input sentence. The input sentence is the cat sat on the mat, and we're going to represent this input sentence as a sequence of vectors, like columnar vectors, vertical vectors, and we can put these vectors side by, like next to each other, to form a matrix. So the input sentence can be represented as a matrix, but if we are not very inventive, we will use these coordinates, the x1, x2, up x1 million, to denote which word from the vocabulary it was. So the word the will be represented with a vector which is very long. It has all zeros and only one in the particle element which corresponds in position to the in the alphabetical order of the input language. And similarly for the word cat, it will be all zeros except for one. So this is the one-hot representation. And there is two main drawbacks of this one-hot representation. First, the vectors really have to be long. And we have maybe briefly discussed this last time. In English, there is about 1 million different word forms. In Czech, you have easily 2 million distinct word forms. So this vector is 2 millions of zeros and one bit in that long list, and that indicates which word it is. So the matrix will be quite narrow and very tall, but all zeros. So that's like it's difficult to work with this this data structure. And the more important problem is that there is no relations. All words are equally close or far from each other. So if you give me two such vectors, like this vector for the word on, and then you give me this vector for the word mat, then all I can tell you from these numbers is that, well, they are different. They have many zeros and this like in the same positions, but the one is here and here is a zero, and similarly or the converse for the mat. So and if you give me then the cat, for example, then the similarity between the cat and mat will be exactly the same as between the cat and on, or the cat and is. So you see that the similarity of words, which could be useful as in a fallback situation. So if there is some input words which you don't know, you have never seen it, if the representation of the word was somewhat cleverer, if it was a kitten, you have never seen kitten in your parallel data, you could see that kitten is related to cat more than it is related to the word because, and therefore you would translate kitten rather as a cat than as because. So your translation would be not precise, but it would be at least related. So the idea of word embeddings is that you convert these one-hot representations to the dense representations. So instead of 1 million, instead of 1 million elements, you would have only 300 to 2000 dimensions, and these would be trained automatically by the network for the particular task. So for machine translation, these embeddings would indicate whether all these words like cat and kitten are most often translated using the same target words, and or whether they are like distinct. Yeah. The famous embeddings that you have probably discussed are language model based. So there's the word2vec or others, and there is two underlying models behind word2vec. One is the SIBO, where you predict the word from its four neighbors, and that's predicting the middle word given four neighbors, two before it and two after it. And there is also the Skibre model, which is mathematically the converse. You predict each neighbor each of the 4 neighbors given the word which was between them in the sequence of words in a corpus. So then in these predictions, you have this input layer, which is the one-hot representation. It's very long. It's as big as the vocabulary size is. And you are predicting also one word in the same like very long vector, but you do it through the hidden layer. And the hidden layer has some much smaller number of elements. So you train the network to best predict the neighbors, and then you extract this layer, the middle representation. And it's up to the network to like use these real valued elements in the vector so that it is the easiest for the network to predict the neighbors. Yeah. So these are the embeddings. They are trained for particular tasks. They are different in machine translation and different for language modeling tasks. So language modeling is predicting a word in a sequence. If when people looked at this, I'm running too late, but I think it's still important. So this is the behaviors of the embeddings. It was illustrated that if you have the word king and you subtract the vector for the embedded man and you add the vector for a woman, then you would get to queen. So there is some geometrical relation between word embeddings. Yeah. Okay. So let's move back to the task of machine translation. We need to process a sequence of English words and get to the sequence of Czech words. If you remember, the SMT already had some problems with the vocabulary sizes of productive languages, such as in Czech, this longest Czech word, or the compounding in German. Neural machine translation, which we'll see in a second, will be doing some matrix multiplications, and we cannot afford to have too many numbers. So the matrices can be only 30 to 80,000 elements long, and that's already too much, but we have millions of word forms. So what can we do? We can break the individual words into some subword units, and then we can use these subword units to put together the words. So we can follow some linguistically motivated units such as syllables or morphemes, but morphemes would have again too long like vocabularies, or we can go for character pairs, or we can go for individual characters. And there you realize that the smaller units you use, the smaller the alphabet. So the smaller the vocabulary size is, but the longer the sequence. And that's why the best methods today are trained on the data. And one of the popular mechanisms is called Bipair encoding. So the Bipair encoding, you specify upfront, I want to use this vocabulary size. I have 30,000 slots. And please populate these slots with either subword units or even frequent words, so that my corpus is broken into the least number of units. So this is like automatic balancing of the vocabulary size and the complexity of the subword units. So frequent words will appear as individual entries in this dictionary, and less frequent words will be constructed using bits which are in the dictionary as well. Yeah, so this is the subword unit representation. Okay, so this is so we have done the first step. The first step is, how do we encode words into numbers so that the neural networks that we have discussed at the beginnings that operate on numbers can digest words. So that was the first step, how to get words into the numeric domain. There is one more thing that we need to do. We need to handle variable length inputs. So the input sentence is not like fixed length, the number of words can vary. So we need the same network to be able to process any length of input. So the technical device that people use in neural networks is called recurrent neural network. And what it does, it uses the same matrix transformation, so some weight matrix W, to process the input one word at a time. So the vanilla recurrent neural network has some state that's a vector representation of what has been digested so far, and it consumes the embedded first token. The matrix tells tells the network how to change the initial state to the current state, and it well, it also emits the state or maybe some output symbol, and most importantly, it passes the state to the next step of the same transformation of the same recurrent neural network. And the second word is digested, and so on. So the same weight matrix is used many times in the calculation. It's like if you remember here at the beginning, we had these layers. So if the weights used here would be used also once more in another layer. So here, this network is not recurrent because all the layers have different weights. But if this network was recurrent, then there would be the same weights reused at every step. And actually, we would be feeding in like the second word and third word in the sentence and fourth word in the sentence. So this whole still is one calculation that produces some output vector, x and y coordinates, or maybe here just one coordinate, the color, and in this calculation, the inputs are gradually like added and multiplied together, so that the output will be the best as expected. Okay, so that's recurrent neural networks. And now the neural language model. So that was the basis. So the idea is that we want to predict the probability of the word given the prefix, the previous words in the sequence. And we can exactly use the neural network for this, the recurrent neural network. We are getting the input, sorry, we're getting the input sentence and this, how to move this way. We're getting the input sentence one word at a time. We use the embeddings. We like look up what is the representation of this word. So we first convert this one hot representation to the denser from 1 million vector elements, we get to 2000 vector elements. Then we use this vector to multiply it with the weight matrix, which encodes the recurrent neural networks. And the recurrent neural network gives us some output state, and this state is as wide as the vocabulary size, and it is a vector of probabilities of all the possible output words. And if we ask which word, which element in this vector has the highest probability, that will be the network's prediction of what is the next word. So I'm sure that you have had normal standard n-gram language models. What were the n-gram language models doing? What were they predicting? So what is the task of language modeling?
Probability.
Yeah, the probability of the next word given
the preceding words.
Preceding n words. So there was a fixed limit. Yeah. Here, the recurrent neural network is producing a vector, and we can this vector is as long as there is the output vocabulary, so the number of all the possible words, and the elements in the vector are the probabilities of each of these words. So if we select the highest scoring element with the softmax the normalization, then we can predict the next word. And the benefit of this recurrent neural network model is that it is like the same network, and you can feed in not just n words, but you can feed in an unlimited number of words. So the neural network has the capacity to learn like infinite long n-grams. So the recurrent neural network is not bounded by the window size of the standard language model. Yeah. Okay, so so you train how to train this network. You feed in the input sentence as a sequence of input tokens. You initialize with random embeddings. This is the same matrix for the embeddings used many times in the computation. You do this recurrent neural network processing, so digesting the word, producing the state, and using the state also to predict the output vector, which is as long as the output words, and then you are checking whether the highest scoring word in this after the softmax normalization is the one that was written in your training sentence. If it is this W1. And if it is the W1, then okay, you don't need to modify the weights. If it's a different word, you backpropagate the error, and you will modify the weights so that the network is more likely to predict the word which you expected it to predict. So when training the network, you are repeatedly feeding the same recurrent, you are feeding the same network with various input sentences, sequences of tokens, and you're asking the network to predict the next word at all positions there. And it is, if it predicts wrongly, you will adjust the inner weights. And after some number of iterations, it will suddenly start predicting pretty well. Yeah, so this is how you train it. And then if you use it then to sample, to create random sentences from this, you feed in the input sentence symbol, you embed it, you ask the recurrent neural network to process it to get the state, and it will produce the state, and it will give you the probability of all the possible output words. You will normalize this with a softmax, and then you will select the high scoring word and select the word. And then you will tell the network, this is the word that you have just produced. Please give me the next one. And the network is trained to predict the next word given the previous ones. So here is the history. Here is the most recent word, and it is predicting a new word again. So the network is repeatedly asked, and it is repeatedly producing the most likely word, and producing a new state at every step. So this is called an autoregressive decoder. It's autoregressive because it looks at its previous output. So it takes n steps to unroll it. It's conditioned on the preceding output. Yeah. So we can skip this. This is just how to implement. It's fairly simple thing, and yeah. And this is yeah. Actually, we can discuss it here. This is the way how to do the translation as such. So you have the input sentence x1 until x4. You use one recurrent neural network, which is called the encoder, to digest all these symbols one at a time. You end up with some vector representation, the state of the state of the recurrent neural network after consuming all the input words, and then you use this state as the initial state for the decoder. And here we have two arrows, and that's two phases of usage. So in the training phase, you are running this decoder network over the output which is in your parallel data. So in your parallel data, you know what is the input sentence and you know what is the output sentence, and you force the decoder to produce exactly the words as expected at the positions where they were expected. So the decoder is simply a recurrent neural network, as we have just discussed. So the same network structure is here used twice. Once you use it to consume the variable length input. Second time you use it to produce the variable length output. The length can be different. It's just a coincidence here that they are of the same length. And the first network is trained to produce whatever sensible representation of the whole sentence, so that the second part of the network produces predictions where the expected word is the most is the highest scoring one. And when you are like checking whether this is the highest scoring, whether the highest scoring word matches the expected word, you are calculating the so-called loss. And if these words do not match, there is some error to propagate, and the network adjusts the internal values so that next time it will memorize better and it will produce the expected output. So this is the training phase. And then in the runtime phase, you process the input sentence through the encoder. You transfer this vector, or you just send this vector to the decoder part. You ask the decoder, given that we are at the beginning of the sentence and we got this sentence to produce, what would be the first word? And the decoder will say, well, this word is the most likely one. We emit it, and we tell the decoder, this was the first word in the sentence, in the output, and this is your state. What would be the next word? And it will say this word, and it will again propose a word. We will emit it to the user, and so on. After some time, it will suddenly say that the most likely word is the end of sentence symbol, and then we will stop asking. Yeah, any questions?
Yes, please, may I?
Yeah.
I was wondering, like the first and the second networks, they're like trained at the same time, or?
Yes, exactly. They're put
but there
together.
Are two different networks.
Yes, there's a different weight matrix in the encoder and different weight matrix in the decoder.
And the training data. So I have like some sentence in Czech, and then like the real translation in English.
Yes,
and that's my
exactly.
training data.
Yeah, this is the parallel data, the same style that we have had last week for the phrase-based extraction. So there we also had parallel corpus, one by one, like sentence for sentence, and we had many pairs of those. In Czech, we have 50 million parallel sentences now, and we train on these.
Okay, thank you.
Yeah. So if you remember from last time, we were doing some word alignment. So we were searching whether this word corresponds to this word or another one. And this time, we are not doing any explicit alignment beforehand. We only train all the weights in the network so that the whole sentence is consumed, and the best and the expected output sentence is produced, and the whole network is totally memorizing it. It is trying to like produce the exact copy of the corpus, the exact same translations, and this is highly inadequate from the linguistic point of view, because you know that there are many correct translations of the of a single input sentence, but the network is simply trying to memorize it. So it's with this vanilla setup, it is quite prone to overfitting. So instead of when you give it a new sentence it has never seen before, it is more likely to produce some related sentence it has seen than to produce the relevant than to produce some translation. So the generalization happens as a random coincidence, so to say. It is trying to memorize the corpus. Okay, the first time this was used, it was used only for short spans of words. So it was used as a scoring function in the log linear model of the phrase-based MT. So in phrase-based MT, there is this variable length phrases, the source side and the target side, and they used exactly this encode the decode the part. So in this case, both the source and target were known, and they used the model to provide a score for that. And this was a highly effective scoring method. So it was very good at predicting whether these phrases are good translations of each other or not. So that was in 2014, but then they used the same setup to really translate full sentences. So by the way, this is an illustration that the phrases then are represented with this C vector, and that C vector has 800 dimensions, and if you reduce it to 2 dimensions, then there is some phrases which are syntactically related. All of them contain of the, so something of the something. And here is another part where are all the countries listed. So there is some similarity in these phrase representations. So we have had the word representations that are created in the word embedding matrix, and now we have the phrase representations, which is the vector representation after the recurrent neural network. The encoder has digested the whole sequence. Okay, so the sequence to sequence approach that first was used as for full sentences is this paper by Ilya Satskever in 2014. They used LSTM, which is an improvement of the recurrent neural network so that it is easier to train. It consumes the input sequence of words to produce a fixed size representation of the sentence. So you have the input vectors, one-hot representation, and there you have the embeddings. So it is all you do is this is indeed just a weight matrix multiplication, and it actually means just selecting one column. The one-hot representation means select one column from the embedding matrix. And what is in the embedding matrix? It starts with random numbers and it is adjusted in the training. So we do not know what these individual elements there are. Some of them can be like how much in the past the word is, and some of them could be how much colorish the word is, and how much bluish it is, and how much cat-like it is. So the elements are unclear, but they are automatically trained, and there is also a combination of elements. So if something is very bluish and somewhat in the past, then it will contribute to the vector representation. We do not know what is in these vectors, but then if we attach the second part, which is the decoder, the decoder will produce the word probabilities. That's the vector as long as the output vocabulary size, and we select the highest scoring word to emit it, and then we tell the network, okay, this is the word that you have produced, and this is your state. Please give me the next word, and it will say this is the most likely output word, and we again emit it, and we train this pair of encoder-decoder networks on the data on the parallel corpus to fully memorize it, and it will learn some network representations. So some continuous space representations of the sentences. So if we look at these continuous space representations, they are here is a picture reduced from 8,000 dimensions to just 2 dimensions. The interesting observation is that here sentences which are semantically closer to each other are semantically closer in this space. So the lower 3 sentences are: she was given a card by me in the garden. In the garden, I gave her a card. I gave her a card in the garden. So in all cases, I was giving the card and she was receiving the card. But the word order is fairly varied here. And here the upper sentences use the same words. I was given a card by her in the garden. In the garden, she gave me a card. She gave me a card in the garden. So actually this in the garden and in the garden, these are syntactically more similar, but they are semantically dissimilar. And then she was given, I was given. So these two are again syntactically pattern-wise more similar, and these are pattern-wise more similar, but still the encoder-decoder architecture, which was trained on English to French translation, decided to put these sentences closer together. So their vectors are similar. Their vector representations after being encoded are more similar than the sentences which are superficially more similar. Okay, so this is the sequence to sequence architecture, and then people use different things in the for this. They can use for varied length input. People can use the recurrent neural networks, which we have discussed. People can use convolution networks, and in 2017, Facebook tried that. Unfortunately, that paper was forgotten or overridden, and all the attention was put to this self-attention paper, the attention is all you need, the same year from Google. So people now use self-attentive networks instead of convolutional networks, but these architectures were probably on par at the beginning. Okay, so let's talk about the attention now. Time is really getting short. We have the other part, so I suggest that we keep talking a little. I'll try not to extend too much into the time of the lab session, but I will to some extent. And then we'll take a break and move to another Zoom call, because this one was supposed to end, and so that we don't occupy it. And then we'll move to another one for the lab session. But let's talk about attention now. So the problem here with this setup is that the varied length sentence is represented with a fixed length vector. And obviously you cannot put a whole sentence into a fixed size vector. So what people figured out was that if they read the input backwards, it actually worked better, because then the vector representation was more it included the first words. It included the first words most recently, so they were like more visible in the vector representation of the whole sentence, and therefore the beginning of the translation was also better and better matched the source sentence. So the best idea was to attend to give the network access to all the possible positions. So the idea that is behind the sequence to sequence with attention, the model which really rewrote the landscape of machine translation, the model that surpassed the phrase-based machine translation, was this attention-based RNN neural network. Here, the RNN is used twice in two directions, left to right and right to left. And you received at the end, this is the end state after consuming the sentence from the tail to the beginning, and this is the representation after consuming the sentence from the beginning to the tail. And you could use these two vectors, concatenate them and use them as the input to the encoder. But then the encoder would still have difficulties to coming back to some middle words. So the idea is that of the attention is that you will, at every time step of the decoder, you will allow the decoder to attend to look at any of these positions. But remember, this is variable length input, and you need to give fixed size representation of this at every step. So the idea is that you will mix these representations with weights, and by doing this weighted sum, you will produce a fixed size representation. So you could like max out, you could maximize all the elements, or you could average them, which is what people do, and you do the weighted average. And what's clever about the attention mechanism is that you modify these weights for the averaging as you go in the decoder. So hopefully it is illustrated here. Here you have the states of the encoder. Here you have the weighted combination, and here are the weights, and the weights are specified by this attention mechanism. And the attention mechanism is a little part of the neural network, and the neural network looks at the current state of the decoder. And based on the current state of the decoder, it says, okay, so you have now, you are at the very beginning. You have not produced any output word so far. I really suggest that you mainly focus on the first word in the sentence. So this would get the highest weight. So all these like vector representations of the sentence are combined together, but the combined vector is most similar to the first position. And then after using this combined information, the decoder, the decoder produces some output word, and it is most inspired by the first source word, and it modifies its state. And again, the attention mechanism is called again. Now the recurrent network state can be will indicate that we have produced one word already, and it would suggest, well, you have already produced this, so maybe look at this second word mostly, but consider also the previous one a little and this one a little. So the attention mechanism like gradually changes what is most interesting in the input sentence as the decoder is producing the output sentence one word at a time. Yeah. So here's another summary of that. This is the input sentence. The words are consumed left to right and right to left. These are the like states of the encoders in the two directions. These states are used in the weighted combination. These are the weights. This is called attention energies. These attention energies are summed together to produce all the information from the source sentence, which is relevant for this particular time step. And the decoder is like rolling over the outputs, producing one output word at a time. The decoder always receives its previous output, and it uses the previous output, it uses the previous state, it uses also the information from the source sentence weighted by the attention mechanism to give us the distribution over all possible output words, and the highest scoring one is the one which we select and emit for the translation. Here is it with formulas. So you have the decoder state, which will be rolling over as I. We have the encoder state, HJ, and we have actually, this is always a combination of the left and right decoders. We have the attention energies, which are calculated automatically by these automatically trained weight matrices. So the attention mechanism knows the current state of the decoder. So here it has access to how many words were produced so far. It has the access to all the encoder positions, and it specifies how each encoder or input sentence position is relevant for the current output position. And this is then normalized, and with these normalized weights, this is the attention distribution, all the encoder states are combined together. So this is the weighted combination over the encoder states, and this is called the context vector. That's the fixed size representation, but now it varies in time as the decoder rolls. So it is like a time varied, but time in terms of the decoder, time varied representation of the source sentence. And then this is the decoder itself. So the decoder predicts its next state from its previous state using some weight matrix, which is trained again, using embedded previous word produced, again some weight matrix to put that information in, and using the context vector, which is the representation of the whole source in fixed size, weighted as the attention mechanism suggested. And there is again some matrix to put that together, and there is also some bias. So this is the next decoder state, and this decoder state is also used to produce the output symbol. So the output symbol is some again some trained matrices. It also has access to the previous word produced. It has access to the context vector, which is the relevant source words at the moment, and it predicts the probabilities of all the output words, and we select the highest scoring one. Here is the attention illustrated as we proceed. So this is the input sentence. Es ist möglich, diese Prozesse in unserem Zone-System, so this is actually subordinates. And this is the output sentence. So, and this is the rows are the attention vectors. So when the first word was produced, the attention mechanism suggested to mainly ignore all the words and focus mostly, so put into the weighted sum mostly the representation of the word S. Then after this word was produced, the attention mechanism suggested to look mainly at the second and halfway at the third word and a little bit on the rest of the sentence. And with this information, ist möglich, and then the rest, the decoder has decided to produce is as the output. And then similarly for the third word, the attention mechanism suggested to look mostly at the third word and somewhat at the second word. And because it was the input word was the input context vector was mainly represented by the word möglich, then the output was possible, and so on. So this matrix is kind of similar to the alignment matrices which you may have produced yourself in with the IBM Model 1 setup, but they are different because they are soft. So every position is represented with a real valued vector, which says to what level, to what extent is that position relevant. It's not like black-white bimodal output. And also it is not relation of the words in isolation, but remember that we were attending to the left to right and right to left encoder states. So this möglich was actually not the embedding of the word möglich, but it was the state of the encoder after having read all the beginning up to möglich or all the tail up to möglich. And that also makes a difference on the presentation. Okay, so that was the vanilla sequence-to-sequence architecture, and I would still like to go over some of the slides relevant for the current model, which is called the transformer model. I will only jump over them, but if you want to know more, there's the lecture for transformer and also syntax in neural machine translation in NPFL 087 class. So you can look at all the details. Yep. This is the sequence to sequence with attention that we have just discussed. And the transformer model is different. I would like to, where is this? Annotate, draw thick and blue. I would like to recommend this block, which is a very simple description of this different shape of the neural network, and I'm using the pictures from that. The idea is that the network is a little bit more complicated. There is 6 layers of encoders and 6 layers of decoders. All the decoders access the output of the last encoder. So internally, each encoder is a self-attention and then a feed-forward, which is the standard transformation that we have seen in the very first slide. The weight matrix, one weight matrix and one nonlinearity function. And the decoder has self-attention, encoder-decoder attention, and feed-forward network again. So what is the self-attention? So this self-attention is a replacement. Where do I self-attention? This self-attention is a replacement of the recurrency or the convolution neural network. So we have the variable input length. We want to be able to access all the input positions. But the problem with recurrent neural networks was that it took them as many steps as this input sequence was long. So you had to wait. The formula of this drawing corresponds to a formula of like putting numbers together and always like applying matrix multiplications and nonlinearity functions and all that. But this formula is as deep as the network, as the input is long. And that is annoying because it takes too much time to propagate this information. So in convolutional neural networks, the idea is that at each layer, you look at a certain window size of the inputs, and with some with a number of steps, you can cover like exponentially many input positions. So the depth of the network is log n compared to the input, given the input length. So the convolutional neural networks are like do not need that many steps. The depth of the network is much smaller than the depth of the recurrent neural networks, and the depth of the network is problematic because the weights do not propagate well in the training. So so the network would be difficult to train if it's too deep, and it also takes time, as I mentioned. Uh, so the transformer network and the self-attention mechanism was designed so that it doesn't need ON processing steps as the recurrent neural network architecture, but only O1 step to attend to all the positions. So the goal here is exactly as with attention that we have discussed before. The goal is to aggregate arbitrary length input vector to some fixed size vector. And this aggregation is data-driven, trainable, and actually trained as we proceed. So that's the goal. So we have the input sentence, inputs x1 till xn, and this is the vector representation, like thinking and machines to input words, and we create three views of them, of these input words. We create queries, keys, and values. So this is three different views of the input words, input word x1, and this is three different views of the input word 2. These views are created by trained matrices. So the network learns by itself what should it look when it's creating a query from thinking, and when it is creating a key from thinking, and when it is creating a value from thinking. If these matrices were identical, then the three views would be the same. And actually, it starts. Sometimes it starts but sometimes they diverge. It's up to the network to decide what is relevant for the key and query and the value. So now, how the keys and queries are used. So the idea is that you score each position with the key and query. So you create a square matrix, and that square matrix specifies how each position is related to all the other positions in the sentence. So it's self-attention. Every position is like self-attending to other positions in the sentence. So when we are thinking, how much the word thinking should be related to the other words, including itself, we always consult the key, the query, and the key for the word. So, and we create a score. So the score here is the combination of the query of the first word and key of the first word. And here's the score which corresponds to the query of the first word and the key of the second word. So this is the 2D matrix of all the queries and all the different keys, and this square matrix specifies how each word is like related to itself and all its neighbors. Yeah, so you get these scores. Then you normalize these scores in some way, and then you normalize them in the softmax so that they add up to 1. So this is the important thing. And then you use these weights. So this is the weights. You use these weights to multiply the values. So you and combine the values weighted by that into the sum vector. So each word, each position, through the keys and queries, has discussed with its fellows in the sentence how much each of these fellows should contribute to my representation. And then I put all of them together. So my representation is again fixed size, and I have as many of these representations as I have input words in the sentence. Sometimes the words, the keys and queries specify that the word should mainly look at itself. So the representation is not too much different from the value of the word itself, and sometimes they can look around. It's up to the network to decide what is relevant. So that's the nice thing about this is that you can quickly calculate this for all the positions at once. So you do you have the representations of all the words in the sentence. You have the representations of all the queries, and you have the weight matrix that creates the queries, and you create all the queries at once. You create all the keys at once. You do simple matrix multiplication to get all the pairwise consultations, like everyone with everyone, and then you normalize it, and you do this again on all elements in the matrix at once, and you use these weights to all the values at once. So so on a GPU, you very quickly calculate this self-attention of all the words, how all the words relate to all the other words in the sentence. So this is the attention mechanism, and the attention mechanism in transform model is actually used 8 times. So if we go to this, yeah, this is a summary. You have the input sentence. You have the 8 different mechanisms. They are technically doing the same calculation, but with different weight matrices. So these are the weights for the head 1, for head 2, and for head 3. Here is the key queries thing combination. So the trained aggregation, and here is the final output vector where you concatenate all the outputs, and then you use one last matrix to squash it to the original size. So this is a very quick O1 calculation, and it allows every word to get in touch with all the other words and change its representation so that it knows about the surrounding words. I can probably, well, this multi-head attention is used 3 times. One is the most common one, or most easier to understand, is the encoder-decoder attention, which is exactly what you have seen in the previous encoder-decoder attentive model. There, the decoder is looking at the various source word positions. But the same style of mechanism is also used within each of these layers of the encoder. So at every layer of the encoder consults all the surrounding words and all the surrounding words and gradually improves the representation of the sentence. And the decoder has also this self-attention. It consults all the surrounding positions. There is obviously some masking needed because the decoder must not look at words which not have been produced yet. Yeah, so if we look at the very original picture, which summarizes the transform model in the original paper, this is the architecture of the transform model. It gets inputs and it embeds the inputs. It uses this multi-head attention, so every word talks to every word. Then there is some normalization. Then there is this little transform that we have seen. This is repeated 6 times, and then the decoder receives this information, and the decoder attends to itself. It's like previous states, and it attends. It includes the information from the encoder, attending to any input word as needed, and then it does the transformation, and it produces after n such repetitions, it produces the final vector of the size of the output vocabulary, and there we just normalize it and select the highest scoring word, and that's the output words, and the output word serves in the next step of the decoder. This is the illustration of the multi-head attention. So this is the multiple heads. This is the values, keys, and queries. And the values, keys, and queries are created from the inputs as we have discussed. And the scale dot product attention is the very quick calculation of the consultations that every word talks to all other words. So this is the transformer model from a high-speed train, and I really suggest that you go over this block again to understand all the details. And one thing that I've skipped is that the self-attention does not know anything about the positions. So every word talks to every other word, and it doesn't know how far they are. So if we did it as I just described, then any shuffling of the words would be totally not noticed by the network. The network has no information about position. So what they do in the transform paper is that they combine the word embeddings with positional embeddings. So they have a vector which is exactly as long as the embeddings, and this vector has varying values as the index of the sentence progresses. So it's kind of like Fourier. I see the Fourier transform there a little, but it's just sine and cosine functions. So in the first element flips the quickest. The last element in the vector flips the slowest as you proceed along the indices of the sentence. And by observing how the elements flip, you can easily see how far are you from the beginning of the sentence, and how far are you from some other surrounding words. So this is the positional encoding, which adds again the lost information about positions. Okay, so that's the transformer model, and this is the multi-head attention when we illustrate it. So on layer 5, remember this is 6 layers, the encoder is looking at its previous representation. So the position which corresponds to the input word it looks with the self-attention weights or aggregates the information from these from all the other words in the sentence, and it turns out that one of the heads is looking at the antecedent of the pronoun. So the network, which was trained to memorize the parallel corpus, it's the same training setup. You feed in the input sentence, feed in the output sentence, and you adjust the weight so that it produces the exact same sentence. It started with random weights and it gradually improves them. After the training, the network in its 5th layer of the encoder, it knows that pronouns should mainly look at the antecedents. So the pronouns are capable of locating antecedents. If you look at another head, then the same pronoun is mostly looking, so the second head in the encoder is looking mostly at the verb which agrees for which this pronoun serves as a subject. So these various heads automatically, just by memorizing the input parallel corpus, these heads find interesting relations. And it was possible to locate a head which corresponded to the antecedent of pronouns, and another head which corresponded to the subject predicate agreement in the clause. if you look at all the heads, then suddenly the picture is not that clear. So you really have to keep searching among these heads to find the interpretable ones, because there is also this other head, this ping head, which links to the verb of the other clause, and there is this head which maps to the verb in the so this is the auxiliary verb in the other clause. This is the content bearing word in the other clause. The clause is the animal didn't cross the street because it was too tired. So it's very hard to interpret all of these heads, but some of these heads correspond to linguistically relevant things, and maybe some of these heads are there are used by the decoder then to say do not confuse that. So the heads can be then used in a negative way. So the network has the capacity to like explicitly ignore some of the information that it has spotted. So it's difficult to interpret this in many cases, but sometimes it is possible. So this is already an example of like another representation. Now the representation is dynamic, it changes throughout the sentence, but the network is learning something which helps it to memorize the corpus well. There is a number of training tricks that you have to apply so that this complex network learns, but it does learn and it translates best. So I do not have these scores here, but actually in these slides, but actually it is sometimes performing better than humans. So I wanted to talk about linguistic information here as well. Let me very quickly summarize that. So I'll stop the annotations for a while. Here on this slide, yeah, I just want to highlight that currently there is little use of linguistic knowledge, explicit linguistic knowledge in current machine translation systems, because the state of the art has quickly moved to the neural setup, and the linguistic is not yet useful. And what people have tried is to constrain the network structure, but that usually leads to worse performance, because if you allow like all connections and if you train it reasonably, that's the hard part though. But if you allow all the connections, the network can choose which connections are relevant. If we limit, if we restrict, if we avoid some of the connections upfront because the linguistic structure, because of some parse tree or whatever, then we are risking that the error in the parse tree will prevent the network from looking at some important position. So constraining the network structure is usually limited too much, so it doesn't perform better than the baseline. The richer input, such as providing information from the parse tree to the network, is useful, but the transformer model with the self-attention can look anywhere, and given enough training data, it is often capable to like construct this richer input by itself. And the last thing is related very much to the deep learning itself. So it's called multitask training. So the network is trained not only to predict the main task, the target sentence, but it's also trained to predict something else. And by predicting something else, such as a linguistic annotation, the network is explicitly forced to consider this linguistic annotation. And that there have been a few papers where this helped, but in the slides that I will very briefly present, some baselines were kind of missing. So here, this is the structure of the network limited by the network that doesn't really work. This is inspired. So here, all the connections are still allowed, and that's good. You can provide the input information at each token. So you can annotate the inputs. The input sentence with additional information, but I told you that the transform model with given enough data is able to locate this information by itself, and you can also do this multitask setup that you are predicting the target output, and where is the annotation? Yeah. you are predicting the target output, and you are interleaving the output words with some linguistic annotation. So here you run the encoder on the input sentence. There are a million different kinds of pizza. The baseline would be that the decoder should be producing the output sentence at one word at a time. Existují miliony druhů pizzy, or one token, it's subword units. And the interleaved setup is that first the decoder is expected to produce the part of speech tag, and then like a detailed morphological tag, and then only then it is expected to produce the word. So instead of existují, it first produced this token identifier, like saying a verb in present tense in third person is to come, and then the word comes in lemma. So then the lemma comes. So if you take this tag and the lemma, then you can deterministically create this word form. And then another tag comes, so the network predicts, and now a noun in nominative is coming, and it will be in inanimatum or whatever gender. And then the word actually comes. So then again, you use this combination, this pair of tag and word to produce the final word. So the network here is trained to go from input sequence of words to output sequence, which is interleaved tag word, tag word, tag word. And the mechanism that we have talked about before, the recurrent neural networks as well as transformer, both immediately learn that they should interleave these two alphabets. They never like do it wrongly. They never produce tag tag or lemma lemma. They always learn precisely to do this pairwise output. And it also helps, it produces a better output than compared to the baseline if you use this setup. So we've tried this with my students. We have used sequence to sequence as well as transform model, and we were predicting target syntax with, I'm skipping the secondary decoder setup with interleaving. And as the tags, we use something syntactic, not morphological tags, but we used CCG tags, if you know combinatory categorical grammar, so this is something syntactic, not morphological, but it is linguistically inspired. And we also used random tags, and we also used a single dummy tag. So the network was producing something like dummy and then existovat, and dummy and million, and dummy and druh, and dummy and pizza. So it was like doing a simple dummy token or a random token, or some linguistically informed token which said the next thing which is coming is a verb which has this valency frame, a verb which expects this noun in prepositional phrase and noun in some particular case or like that. So this is what we did, and here are the results. This is predicting target syntax. Let's look at only the interleave setup, only the left-hand side plots. So the this is sequence to sequence, and this is the transformer setups. So only the left-hand side plots are important for us. So if the network was expected to produce the dummy and then the word, then it didn't learn at all. So producing the dummy token was too easy. The network specialized in excelling in predicting greatly this dummy trivial token, and it was too bored to learn something like translation. So the same tag, that is really bad idea. If you use the baseline, then you got this performance. So baseline is not to predict anything, predict just the sequence of words. The CCG is producing the linguistically informed setup, linguistically informed tags, and the random tags actually fare better. So here the linguistics, there was a paper which said use linguistic tags, it will improve the performance over the baseline, and we said yes, that works. But if you use random tags instead of linguistics, that will work even better. The reason here is that probably the network, with this extra step of producing something, it's actually a garbage token. It cannot succeed with this garbage token. The network gets some extra thinking time. So it's like a deeper decoder. The decoder has extra layers of information to think about the output, to produce a better choice of the output word. And that is more useful than learning to produce the linguistic annotation at this position. The same, no, so not the same. So for the transformer model, the random tags are equally important. They're very good compared to the baseline, and a tiny little bit better output was produced by the CCG tags. But for most of the training, the CCG tags were actually not better than the random outputs. Yeah. So the main message to take from this is that machine translation has jumped ahead with the deep learning. The transformer model is very clever to pick up all the important information anywhere in the sentence. So providing an upfront is not too useful. And training the network to produce it with this multitask training is useful, but you have to be very careful to make a comparable comparison because dummy or because random tags can like work better there. We have another setup with the attention mechanism where we were training transformer. So this is the transformer. It has the 6 layers of the multiple heads. And we have noticed that the heads can be interpreted as dependency tree. So if the attention head says how much each word looks at some position, we can treat this as information like who is my governor in the dependency tree. So this is what we did. We actually trained the network to not only to translate and use the heads as it desires, but also to use one of the heads, we choose any of those, they are like equivalent at the beginning of the training. We choose one of the heads to predict the dependency tree. And we were checking whether the network, so we were scoring the network in the training, how well it produced the exact expected output sentence, and how well it produced the source sentence dependency tree in its first head on one of the layers. This is the output of the this is the scores. So when we ask the network to produce the dependency head on this layer number 1, so the second layer, it performed best. And it improved the baseline quite a bit. So we said, oh, great, that's amazing. We know how to improve the translation using transformer model. We will ask transformer to predict the source dependency tree in its second layer head. Using other layers was not so good anymore. And if we measured how well it is parsing, so if we like train the network, then the parsing accuracy is actually higher if the dependency head is if the dependencies are expected from some deeper layer, not the shallower layer. So if you want transformer to train for parsing and translation, if you want to focus on translation, demand the parse from a lower layer. If you want the transformer to focus on parsing, demand the parse from a deeper layer. So this is kind of natural thing. But then we had one more experiment, and that like killed our joy for linguistics. We have asked transformer to produce the linear tree. So the tree is just telling that every word depends on its preceding word. So it's just linear. It's a sequence. It's not a tree. And this like stupid linear tree actually helped better. So with this dummy parse tree, we got a better score than with this informed tree. So again, the message is, yes, linguistic can seem important. It can seem to help over the baseline, but you need to try some dummy baselines as well, because you can get the benefits, you can get maybe better benefits with the uninformed setup there. So this is yeah, I will provide you with links to this, or you can follow the link in the slides there. I'm slowly finally coming to the end, so I'm skipping the outputs. Neural networks are obviously making errors, and let me just summarize that the ultimate goal of the classical statistical machine translation is to find some minimum translation units. These can be graph partitions if it's a tree-based mechanism, or they can be like short phrases, just linear separation of the inputs. And these translation units should be frequent enough across many sentence pairs, and they should be easy to work with, easy to reorder, and we should be able to find them in some unsupervised fashion, ideally. So that's the basis of phrase-based MT. But there is the independence assumption of these translation units. And the independence assumption is not at the neural network style of processing. There you are avoiding the minimum translation units, and instead you are finding a neural network architecture which reads the inputs in as original form as possible, and produces the outputs, and it's trainable in end to end. And we have discussed the recurrent neural networks, so encoder decoder architecture with RNN there, and the attention mechanism, so that the decoder has a chance to look at any of the positions in the input sentence. And we have also talked about the self-attention mechanism, where there is not this slow, like step-by-step consumption of the input, but at every step you can look at all the possible input positions. So in sum, over these 2 lectures, and sorry for the second one being too much extended, we have discussed what makes machine translation statistical. That is the seek for a good modeling of how to produce the most likely target sentence given the source. And we have discussed the 2 crucially different models: the phrase-based, where the phrases are contiguous and independent of each other. There was the Bayes law and the log linear model, the handcrafted features, the scoring functions. Some of them were local and non-local, if you remember. There was this decoding a search, expanding partial hypotheses by attaching the puzzle pieces to them. And then we've discussed the neural approach, which is like translation unitless. It represents, it uses the continuous space for various intermediate representations. The basis is that neural network, NMT, is just a fancy language model, because the decoder is predicting one word at a time. So it is only like a language model conditioned on the source. We have discussed the word embeddings, the subword units, the RNNs for variable input length and output length, the attention in the attention model, and the self-attention. And we have discussed how are linguistic features doing in neural machine translation these days. But I hope that we'll still be able to come to phase where linguistics would be explicitly useful. And but it's hard to say what is good. Like speakers of language do not necessarily have any linguistic background. We get it to some extent at school, but only to a limited extent. And it is sufficient for us to learn how to translate. So it's not too big surprise that there was that people found a neural network architecture which learns to translate without getting this explicit knowledge. So maybe we can get like more elaborate output, higher quality output, if we add a little bit of linguistic knowledge, the similar style of knowledge that people are getting at schools to the transformer network. But as of now, it is not necessarily needed for the best translation quality.